this week you have to, if you're going to measure the efficiency is mechanical power. That's what comes out, and you put some electrical power in, right? And so that you need to somehow measure this, you need to somehow measure that, right? The electrical power, we know if we just have a resistor and we have some constant voltage here, say at 10 volts or whatever it is, we know the power in the resistor is just 10 volts squared over R, right? So you know how to calculate the power in your, well, let me just say, you generally made something which might have a coil of wire. You made something like, many of you made something like that, and that's an electromagnet, right? And the probably, certainly there's a resistance in the wire. And I think it probably what most of you made, I can't guarantee this, but most of what you made, this is negligible. And the easiest way to think about it is, something like this. And what you're putting in here generally is some kind of sine wave. You have some V amplitude sine omega t. So same thing here. And VR, the voltage on your resistor, then will be V amp sine omega t. The current in the resistor will be V amp over R sine omega t. What's the power in the resistor? We've got water coming off a waterfall, the voltage is the height, I is the current. So the power at any time would be I of t d of t, so V amp squared over R, sine squared omega t. So we've done IV all the time, but now we have time dependence, let's get the sine squared. So sine squared is sine squared. Well, let me just write this. Sine squared omega t. Good, right? And so what's the average amount of power that comes out? Well, for example, at this point, the power of the resistor is equal to 0. And here the power of the resistor is V amp squared over R. So what would be the average power in the resistor? You've got a power which goes from this value up to this value, back down and up again. So the average is somewhere in the middle. What's the average value of sine squared? You know this one. Half, right? The average value of sine squared is a half, just like the average value of cos squared is a half, because you know that the sine squared and cos squared you have to get 1. So the average power then would be the amplitude squared over 2. So all I want to point out is there's a factor of 2 in here because the voltage is not always the maximum voltage. The voltage goes up and down, so the power is not always at its maximum value. Anyway, that's one way you can approach your electrical power. How can you measure mechanical power? Something's rotating. No idea? Somebody had thought about it for a laugh. Somebody had laughed in a few hours, right? Say I have a motor and it's turning a shaft, and I'm using, I want to know what kind of a mechanical power I can get out of that shaft. So my piece of chalk is rotating. Let's see, if I have just an infinitely thin piece of chalk, or something rotating at constant speed in a circuit, is it doing any work? If I have a wheel and it's just rotating with no friction, is there any mechanical work or any mechanical power? For example, once it's rotating, we don't have to put any power in. No. It's nothing to do with this course. Let's go back to 151. I have something here, and maybe it has something on the end of it, and it's rotating with no friction. This whole thing is rotating with no friction because it's on some kind of bearing that holds it without friction. Once it's moving, do I have to put power into it to keep it moving once it starts going? Nice ball bearings and just go smooth. No, why not? Something's rotating, or does it keep doing all by itself? It keeps rotating as angular momentum. So it's not doing any work. What would work mean? When would our shaft be doing something? And why do we turn a motor? Maybe we attach it to a wheel and we accelerate a car. And then the car goes from 0 velocity to some other velocity. That means we added mv squared to the car. So that would be work. So if you make a shaft turn, in principle you could put a wheel on it. And watch the whole thing get up and move. You could have flexible wires, and you could figure out the velocity, how fast it accelerated, and how much mv squared went in some amount of time, and that would tell you the work that came out of the motor. But that would, you'd have to put big tires on each end, so the whole thing is lifted off the ground, and have flexible wires, and you can watch the thing move. Then you go from 0 velocity to some velocity, that means you're getting work out of your motor. How about something simpler? If I didn't want to put big wheels on my car, there you go. What else could you do here to make that spinning thing do some work? For example, how could it lift something up? If I gave you a spinning shaft which said lift a weight, what would you do? It's a design problem in 151. Again, this thing is rotating, and I say, move a weight up off the floor. Yes.
Just use a pulley, attach a string to a pulley system.
Okay, good. So you could tape a string on and hang a weight here. And then how do you get the work done by the motor? Meaning the energy, mechanical energy is a function of time. What do you measure? I want some mechanical power, energy over time that the motor is doing. So how do you follow up on that, Max?
How would I follow up on creating the power?
Well, you said that if I turn the motor the right way, the string goes up, right?
Yeah.
The weight goes up.
Mhm.
So what's the rate of energy I'm adding to the weight?
Would it be 1/2 mv squared? 1/2 mv squared or no?
Okay, and then once it's going at a constant rotational speed, what the velocity would be accelerating or constant?
It'd be constant.
Yeah, because most you design a motor, there's some magnetic field that's changing to cause the motor rotate, it would go to a constant speed.
Yeah.
And then once it's at a constant speed, then the velocity is not changing, you agree?
Yeah.
Is the motor still doing work?
Yes.
Because,
Because it's still lifting the weight up. It's still lifting the weight up.
yeah, so good. So how much work is it doing? If I'm going up, we have dH, dt is the rate of height versus time.
How much work are we doing is the question?
Pardon me?
The question's how much work are we doing?
Yeah, how much, which means mechanical energy versus time.
Okay.
So if I go from height 1 to height, so here's H1, and the thing goes up to H2, how much mechanical work did I do? This is, go back about 4 months.
Go up if you want. It'll be MGH, right?
Yeah, mg, change in H.
Yeah.
Okay, I lifted a weight from height 1 to height 2, right? You guys done that a long time ago. Good, so you have a height, right?
Mm-hmm.
So there you go. You have a way to measure some mechanical work, right? For example. Some of you may have made things that just push something once. So something was, well, let's see. Let's say it just pushed something one time. It was standing still and then it moved. In that case, it's not continuously happening. You might have some mass and its velocity versus time. So you flip the switch and its velocity goes up, and then over time it slows down. Because that mass moved and then it slid. How could you figure out the total amount of, in this case, how could you figure out the total amount of energy you gave to the mass? Let's see, let's call this is velocity versus time. What's the total energy? Well, here we decided the energy of the mass is equal to 0, and here it's got some kinetic energy, right? So what would be the kinetic energy of the mass? Let's see, we turned on the motor, and we turned on the motor here, the mass sped up, and then the motor turned off, and the thing just slowed down. So the kinetic energy would just be 1/2 mv squared. How would you measure velocity? Yeah?
Pardon me? Have what?
Oh, you have laser gates, yeah, that'd be kind of complicated, just something you can easily do in a lab. Maybe take a movie with your cell phone, and you play it back slowly, and you could somehow get the velocity out of that. So you have to come up with some ideas. If somehow you have to measure mechanical energy. And well, back 4 months ago, I think how you would have done it, and that's what you have to, do this week. Okay. All right. Questions? All right, what I want to do today is finish up this discussion of bandwidth we had on Friday. It was rushed at the end. And